So this video is going to be an introduction to graphing quadratic functions. You've probably graphed some functions in the past, like a linear function, f of x equals 3x plus 2, or like y equals mx plus b. But we know f of x is synonymous with y. It's just function notation where you see the input and the output. So anytime you want to see what a graph looks like, you can create a table. This is kind of a good start. Then we'll learn other methods on how to graph, like when you learned linear graphs, you learned, oh, I can just plot the y-intercept and do the slope. But an option to graph anything, so if you don't know what it looks like, is to make a table. So we're going to do that with f of x equals x squared. Now this is what we call the parent graph. Like it's the most basic quadratic graph you could do. There's no transformations. It's kind of like your base graph. So if the input's -3, my output, f of -3, is -3 squared, or 9. So if the input's -3, the output is 9. So -3, 9 is a point on my graph. And you know what? When I plug in 3, I'm also going to get 9. So if I plug in a negative number, I'm going to get the same thing as the positive, because when you square it, you always get the positive result. So -3 and +3 have those points of, those outputs of 9. If I plug in -2, -2 squared is 4. Same thing with 2. 2 squared is 4. So I'm going to have the point -2, 4. Oops, too low. -2, 4, and +2, 4. If I plug in -1, I'll have an output of 1. And you might be like, why are you squaring it? Well, that's what this function rule says to do, and I want to see what the graph looks like when it says take the input and square it. So I have -1, 1, and +1, 1. And then I'm going to have 0, and 0 squared is 0. So 0, 0. Now these integers aren't the only numbers I could plug in. Like I could plug in whatever I want. I could plug in a half. I could plug in -3/4. I could plug in -1 1/4. So we're going to connect these points, and they create a curve. They create a parabola. And lots of things in nature make this shape. Like if you throw a ball, it makes an upside down parabola. And you could model that with the function, the mathematical function x squared, or some sort of variation on x squared, whether the parabola is higher or fatter. So let's go back to talking about the domain and range of functions. That's what this is asking us to do. This is something we did earlier in the year. Now remember, domain is a list of all your x's, and a range is a list of all your corresponding y's. Since I can't just name every x, because there's actually infinite number of x's. See this arrow? It's covering x's all the way to -infinity. Even though we're really focused on it going up, like if I'm thinking about what x values it's covering, it's going all the way to the left. So my domain is saying I have x's from -infinity, and then I continue to have x values forever to the right, which is +infinity. Now my range is your y's. So you want to list it as your smallest y value to your biggest y value. And we taught you that you kind of like look at it coming from underneath, and there's my smallest y value. And then I have y values all the way up to infinity. So my range is going to be 0 to infinity. And actually every quadratic function is going to have an unbounded domain. Unbounded meaning there's no lowest or highest. It's always going to be -infinity to infinity. So this will always be the same. The range, however, is going to change. It's going to have either a minimum point, like this one, or a maximum point, like if it was upside down. And we'll get into that. Now, not every quadratic function looks like this. Sometimes they have what we call transformations. Like this one has 3 terms, negative x squared minus 4x plus 1. And I'm going to quickly plug in negative 5, negative 4, negative 3, negative 2, negative 1, 0, and 1 to show you what this looks like. But I'm going to pause and do it. So if you want to pause and try it on your own, you could do that. So I plugged in each x value into the function, making sure that when I do a negative, something negative squared, that would become negative 25. Minus 4 times negative 5, that would be plus 20 plus 1. And that's how you get the negative 4, and I did that for each. So now I'm going to graph these as coordinates and then connect them with a curve. And you can see the symmetry on these. I can see there's kind of symmetry down the line right here. So that's important. It's like a mirror image, like a butterfly. It has that line of symmetry where it's the same on the left and the right. Now this one's facing down, and the thing that made it face down is actually this negative out here. The fact that A, my leading coefficient, was negative made it face down. So parabolas can face up, they can face down. Putting in these values might make it wider or narrower, and we can see this was kind of, it's facing down and shifted left and shifted up. So before we get into, okay, how do I find these, how do I graph these without just plugging in a bunch of points? Because there are just like key pieces of the parabola that we need to graph. Let's talk about what those key pieces are. So I'm kind of saying like the anatomy of a parabola, the different components to it. So this point is very important. It's called the vertex. Kind of like how an angle has a vertex, a parabola has a vertex. So this is the vertex. Sometimes it's noted as h comma k, just in general, but it's a point. So realize that the vertex is a point, an x comma y, or sometimes we say hk, but it is a point. So this is the vertex on this parabola. This is the vertex on this one. So that's negative 1, 4. So that was the vertex. A parabola also has an axis of symmetry. And it's a vertical line. So this red vertical line is called the axis of symmetry. Kind of like an x-axis or a y-axis. This is a line, so this is a vertical line. That is your symmetry line. You could fold the parabola in half at this line and it would completely overlap. Because it's a vertical line, so here's some memories. You write it as x equals a number. Now that number is going to be the same as the x value of the vertex. Like whatever this is the same as your axis of symmetry. So for us, our axis of symmetry is x equals negative 1. So we found 2 important components, or identifying them. The vertex is a point, negative 1 comma 4, negative 1 being the input, 4 would be the output. Like notice if I plug in negative 1 into my function, I will get 4. So that's why, negative 1 comma 4. And then the axis of symmetry is x equals negative 1, the same as the x value of the vertex. So some other key components is I have x-intercepts. So I'm going to do those in green. So you're going to have x-ints. They are coordinates. So it's the point 3, negative 3, 0, and 1, 0. Y is always 0. So it's like, what's the input such that the y, like the output would be 0. And we're actually going to find those in the future with the quadratic formula. So that's cool. And then the last thing I want to highlight is what color do I have left? Blue. The y-intercept. Something you're very familiar with. So it's always 0, comma, a number. In our case, it's 0, 3. So you've got the axis of symmetry, the vertex, the y-intercept, the x-intercept. And these are all your key features to a quadratic function graph. So instead of just plugging in a bunch of points, what we're going to do is just find these important features. We're going to talk about how do you find the vertex algebraically from the equation, the axis of symmetry, the x-intercepts, and the y-intercept. To find all those pieces, plot them, and get the graph that way. Okay, so check out the next video to see how to find the vertex and the axis of symmetry algebraically.